Okay. Let me share the presentation. Okay. Okay, so what we were talking about last time is that there are ways to compute the linear convolution during the DFT, using the DFT. And the reason why we want to do this is that there are very efficient algorithms to compute the DFT called fast Fourier transform, or FFT. And we use these to compute the linear convolution. So the idea is that we compute the DFT of the two sequences. We do the product in the Fourier domain. So we compute capital X3 as the multiplication of capital X1 and capital X2, the two DFTs. And then we use the inverse discrete Fourier transform to compute the convolution of the two sequences. Okay? And the multiplication in the Fourier transforms corresponds to the circular convolution. But what we want to obtain is the linear convolution. So to obtain the linear convolution, we must be sure that there is no aliasing in time in the circular convolution. If you remember what we have seen last time, so we have seen that if we do the linear convolution of two sequences like this, two rectangular sequences, the result of the linear convolution is longer than the original sequence. And in particular, if the two sequences have same lengths, the length of the linear convolution is 2 times the length of the original sequence minus 1. Okay? So if the length is L, the result of the linear convolution is long 2L minus 1 points. Okay? And then we have seen that if we try to do the circular convolution on the same number of points, we will obtain a result with aliasing, which is different from the result without aliasing. The result without aliasing being the same of the linear convolution, and if the number of points of the circular convolution is too short, there will be some aliasing in time, and we cannot reconstruct the linear convolution. Okay? So then I gave you this example. I will not spend too much time because it's something that we have done last time. So if you have two sequences of lengths L and P, the result of the linear convolution will be L plus P minus 1. Okay? And so to obtain a circular convolution that is equal to the linear convolution, we must ensure that the number of points on which we do the DFT and then the inverse DFT is at least long L plus P minus 1, being the L and P the lengths of the two sequences. Okay? So if there are no questions about this, I will move on to the new lecture for today. Okay, share again. Okay, so let's consider a sequence that is L points and a sequence that has P points, which we call X of n and H of n. And we said that the linear convolution has finite duration with length L plus P minus 1. All right? right? So for the linear convolution and the circular convolution to be the same, the circular convolution must have lengths of at least L plus P minus 1 points. Okay, this is what we just said. And so the original sequences X and P, X and H, must be increased or must be augmented with a sequence of zeros. So we artificially prolong the sequence so that the length is L plus P minus 1. And this process is called zero padding. So we add zeros to the length, to the original sequences. Okay. In principle, you can add as many zeros as you want, but at minimum, you have to add L plus P minus, you must reach L plus P minus 1 points, okay? So this is easy if we have two sequences that have finite lengths. But many times, we have sequences that are not finite or very, very long. So for example, if you have a movie that is 2 hours long, in principle, you should do, if you apply a filter, you should compute the convolution with the data, with all the data you have. And if you are doing a streaming, for example, of data, and there is no, in principle, no duration, it's infinite, then in principle you have to store all the data and then compute the convolution on all the data. And of course this is impractical. First, because you have problems of memory, and second, because you have to wait to obtain the result. Okay. So it's computationally also very difficult to calculate the convolution on all this data. So the solution to this problem is to do some convolution in blocks. Instead of computing the convolution on the entire data, we split the data in blocks and we apply what is the so-called block convolution algorithm. Okay? And this is what we will see today. So the sequence is cut in segments, and each of these segments is then convolved with the filters, and then all the blocks are fitted together. Okay. How is not obvious, because as I said, the convolution increases the length of the sequences, right? So all the blocks of the original sequence, when you do the convolution, all the single blocks are longer than what they were before, all right? And so how to fit the blocks together is done in mainly two ways, using the overlap and sum method or the overlap and save methods, okay? So let's consider first a finite length sequence h of n and an infinite length sequence x of n. Okay? The sequence h of n, it has length p, and the second sequence, which is infinite, we split in blocks of length L. Okay? And so the infinite sequence is segmented and is can be indicated as the infinite sum of blocks v x of v, okay, of n. So these blocks x of v are defined as x of n truncated. Okay, so x of n multiplied by a window, basically. Okay. So in the overlap and sum method, if the sequence h of n has duration n, the convolution of the original sequence x of n and h of n can be represented with the blocks x of v. So we start from the definition of the convolution. Now the convolution should be the infinite sum, but here, since h of n has only duration n, the summation goes only from k that goes from 0 to capital N minus 1, okay, of h of k, x of n minus k. So if we substitute the different blocks, we have the summation of h of k times the summation of the segments. So v that goes from 0 to infinite of x of n minus k of v. Okay, I'm just substituting the x of n as the summation of the blocks. And if we swap the two sums, what we get is the infinite summation of the summation of h of k times the single block. And if you look, the last part, the internal summation, is basically the definition of the convolution, the linear convolution between h of k and the single segment, okay? So we have an infinite summation of the result of a linear convolution on a finite length, okay? So now what we get a sequence of lengths n plus L minus 1. So we have the linear convolution between these two finite length sequences, x of v and h, and the result will have lengths of n plus L minus 1. And then the support will go depending on the block, okay? So for example, the first block, so for v equal to 0, will have support from 0 to L plus n minus 2, okay? And if v is equal to 1, the first point will be in L, okay? And the last point will be in 2L plus 2n plus minus 4 and so on, okay? So the blocks overlap on a certain range, and the range will be the one that is indicated here. So the overlap, the important thing is that there will be an overlap only on two blocks under the condition that L is greater or equal than n minus 1, okay? So here is an example so that you can visualize better. We have the first block, x of 0, that goes from 0 to L. The second block, that is also length L, but starts from L plus, from 0 to L minus 1, the first one, and then from L to 2L minus 1, and so on. And then when we compute the linear convolution of the blocks, the linear convolution will not stop at L for the first block, for example, but to L plus p minus 2, okay? And this overlaps with the second block. And then we compute the convolution on the second block, and the lengths will be overlapping with the third block, okay? And so on. Is this clear for everybody? Are there any questions? So on top you have the original blocks, which are the segments of the original sequence. And on the bottom you have the result of the convolution of the single blocks. Okay? And these blocks, they overlap at least with the next block, at least. But if you don't do things well, it can overlap also on multiple blocks. And the condition for overlapping only on one block is that L must be greater or equal than n minus 1. Okay? Is it clear for everybody? Okay. So, in the overlap and save method, we consider the two sequences. I'm using here lengths n and m, but it's the same thing, to compute the circular convolution. Okay. So the values for which it is not necessary. Sorry, just another thing for here. Of course, in the points that overlap, we have to sum the samples. This is why it's called overlap and sum. All right, because here what we obtain is that the result of the linear convolution is the sum of the blocks that are on which we compute the convolution. Okay, so here we have some points that are exactly the same of the linear convolution on the entire sequence, and some other points that we have to sum together to obtain the result that is the correct one. Okay. So if we want to compute the convolution on the entire sequence, we can do the convolution in blocks, but then we have to sum the parts that overlap together. This is why it's called overlap and sum method. Okay. Let's consider two sequences in general of lengths n and m, and we want to compute the circular convolution this time. Okay. Now, the circular convolution, as we have seen last time, is defined modulo n. So the length, if the convolution is on n points, the length of the length is on n points. Let me check. The length is on n points, but the sequence is of length m. So we have to sum then all the points, and the sum is done over modulo m. Okay. So the points that are the same of the ones of the linear convolutions are the ones for which n minus k is between 0 and capital N minus 1. And the reason is that if it goes outside or above n, capital N, then the modulo operation overlaps on the first part of the sequence. Okay. So this means that we must have the good points, the ones that are the same between the linear and the circular convolution, are the ones between m minus 1 and n minus 1. Okay. So the points in this interval between n minus 1 and n minus 1 are the ones that are the same between the circular and the linear convolution. So from the subsequences, we have to extract those points that are between n minus 1 and n minus 1. Okay, this is the overlap and save method. Sorry, I got confused. Okay, so this is the overlap and sum, and this is the first method. The second method is overlap and save. I got distracted, sorry. In the overlap and save method, it's different because we are computing the points that are the only ones that are good in the sense that they are the same of the linear and the circular convolution. Okay, so we have to compute only those points that are the same between the circular and linear convolution. How do we know that these two points are the same? As I said, are the ones that do not go above n minus 1. And so this translates to the condition that m minus 1, that n must be between n minus 1 and n minus 1, okay? So the sequence, the parts of the sequence that are good, are not overlapping, are the subsequences of x of n truncated between n minus m plus 1 and n plus n minus m plus 1 times v. So I will show this graph so that it's a bit more clear for you, I hope. So we identify the parts that are identical to the linear convolution. Okay? So if an L-point sequence is circularly convolved with a pinpoint sequence with p less than L, then the first p points are incorrect. Okay? So here on the right, what you see is the result of the linear convolution again. Okay? But the first part is not correct. Okay? So we discard the first part. And we move forward. Okay? We move forward in order to compute only those points that are correct. And we store those points. And the other points we throw away. So here, what we're doing differently from the other, from the previous overlap and sum, is that we are storing only the points that are correct. We do not have to sum the different parts together. The advantage of this method is that since there is no connection between the segments, each computation is independent, we can do this in parallel. We can parallelize the computation of the single pieces because you don't have to combine the pieces together. Okay, I don't know if it's clear or not. Are there any questions? So here it's a bit different because we don't do the blocks of length L. We move in a different way. We move a bit. We overlap in the computation, not in the result. In the previous method, in the overlap and sum method, we have the blocks one by one, and then we overlap in the computation. Okay, and here, and then and we overlap in the sum. And here we overlap in the computation, and then we discard the points that are not good. Okay, is it clear for everybody? No. For sure, you can find more information in the book or in the lecture notes, but I think apart from what I already shown, this is basically the idea of these two methods. And then what I want to start today is to actually see some discrete time systems. Okay. So this, what we have seen up to now, is more or less the mathematical foundation to now analyze discrete time systems. And a discrete time system is a mathematical operation or a mapping between an input sequence and an output sequence. Okay, we can use the symbol T to indicate this transformation, or we can use a block diagram to indicate this transformation given by the discrete time system. An examples of discrete time systems are the moving average, So, for example, the sum of different points. Another example is the maximum of different points, or the ideal delay system, which is y of n equal x of n minus n0 for n0 in integer. Okay, these are just a simple example of discrete time systems. Let's see some particular type of discrete time systems. The first category is memoryless systems. A memoryless system is a system that has an output that depends only on values that are from the past, or from the present. So y of n, the output, depends only on values of x of n with the same n. So an example of memoryless system is the square function or the sine function. And a counterexample that is not a memoryless system is the delay system. Okay, the delay is not memoryless, of course, because it has to has the memory of value of the past. Another type of systems are linear systems, and a linear system is linear if and only if it has the property of additivity and scaling. Additivity means that the output would be the same if we consider the input separate and we sum the result, or we give the sum of the inputs and we obtain the same result. And scaling means that if we modify the amplitude of the input, the output is the same, amplified by the same quantity. Okay, so a system is linear if it has both this property of additivity and scaling. Let's see an example. For example, the ideal delay system is a linear system, of course. And if we look at the combinations of ideal delay systems, it has the properties of additivity. So if we consider the sum of the inputs, then the outputs will be the sum of the same outputs, and the same if we consider the outputs of the two inputs separate. And also it has the scaling property. So if we consider the output of the input times A, it would be the same of multiplying A times the output without A. Okay, this is quite straightforward. A special category that is of interest for us is the time invariant systems, or also called the shift invariant systems. And the characteristics of the systems is that if we shift the input, the output will be shifted by the same quantity. Okay. So an example is the square function, which is a time invariant system, because if we consider the delay of the input, we have a certain result, and if we delay the output, we have the same result, basically. Let's see a counterexample. A counterexample is the compressor system. So if we consider the input delayed, it will be as a result. If we consider the output delayed, it will correspond to the different input. So the compressor system is not a time invariant system. Okay, is it clear for everybody? Also, another important category is the causal systems. And the system is causal if its output is a function only on the current and previous samples. So it does not depend on the future. Okay. A causal system depends only on the present and on the past and not on the future. A simple example is the backward difference system, where the output is the difference between the present sample and the previous one, and an anti-causal system or non-causal system is the forward difference, where we have the combination between the present sample and the next sample, the future sample. Okay, this is not a causal system, it's an anti-causal system. We are interested in causal systems because, in general, in real systems are causal. They don't depend on what happens in the future, but depend only on the present and the past. Okay. Also, another important category of systems are the so-called BIBO systems. We called BIBO in the sense of bounded input and bounded output. If a system has bounded input, it is stable in the BIBO sense if it corresponds to a bounded output. Okay, so a system is stable in the BIBO sense if and only if every bounded input produces a bounded output. Okay. Again, an example of BIBO stable system is the square function, because the input, if the input is bounded by a certain b of x less than infinite, then the output is bounded by b square of x. Okay, so it's a BIBO stable system. A counterexample is the log function, because the logarithm, even if it's bounded by b of x, the input, the output is not bounded for x of n equals 0. Okay, so if x of n is equal to 0, y of 0 of the logarithm is minus infinity. Okay, so even if the input is bounded, the output is not bounded. Is it clear for everybody? Are there any questions, comments? Most often we will encounter, or we will study in this course, linear time invariant systems. And the importance of this system is because of the mathematical tractability. Okay, and most signal processing applications involve linear time invariant systems. The reason why they're important is that they can be completely characterized by the impulse response. So if we consider the impulse response, so we have an input which is delta of n minus k. The output is the impulse response indicated with h, called impulse response h of k of n. So any input can be represented with as a multiplication with the delta, actually the convolution with the delta, and we obtain that x of n is equal to the summation of x of k times delta of n minus k, for k that goes from minus infinity to plus infinity. And the output, if the system is linear time invariant, as you can see, is the result of the output of the deltas. Okay, so this is why it's important to study linear time invariant system, because it's basically the output is the convolution of the input with the impulse response sequence. Okay. Is it clear? Okay. So let's see some examples of a linear time invariant system. We have a linear time invariant system that has a certain input, for example, a delta, and the output will be, of course, the impulse response, which is, in this example, equal to 1 for 0, 0.5, and 0.25, and the rest is 0. So this is an example of the impulse response of a system, of an LTE system. Now, okay, so in the second row, in the second image, what we have is that if we double the input, the output of the linear time invariant system will be the same, but double in amplitude. Okay, and this comes from the scaling property. If we shift the input now, the output will be shifted by the same quantity. Okay. And if we have the combination of the two inputs, the result will be the combination of the two outputs, the sum of the two outputs. All right. So this is why this seems pretty obvious, but it's obvious only for linear time invariant systems. This is valid for linear time invariant systems. And this is why we're interested in this type of systems, because they are very easy to understand and to modelize. So the properties that I've just shown is that since comes from the properties of the convolution. So since the convolution is commutative, you can look at the output as the input convolved with the impulse response, but you can also see it the other way around as the input that is h and the impulse response that is x. So you can interpret the output not only as the convolution of the input with the impulse response, but also as the impulse response as the convolution. And you can think of the system of a system with impulse response that is x of n. You can swap the two, x of n and h. And also, the convolution is distributive. So instead of analyzing the two sums of two subblocks, you can interpret as the same block with the summation with the sum of the two impulse response. Okay. So these are basically the properties of the linear time invariant systems. Okay. And you can also think of the cascade connection of LTE systems. And in the LTE systems, you can swap the blocks together, and the result will be the same. So it doesn't matter if you have first H1 and then H2, or first H2 and then H1, the result will be the same. And you can also put them together in the same block, considering the convolution of the two blocks. Okay. Let's see now the conditions for the stability, the Bible stability of LTE systems. An LTE system is Bible stable if and only if the impulse response is absolutely summable. Okay. So if the impulse response is absolutely summable, then you have that the output is in amplitude, the amplitude of the convolution, of course, between h of k and x of n minus k, and this will be less or equal than the absolute of the two sequences of the elements multiplied. And if the input is bounded, Then you can substitute the bound, and the output will be bounded by b of x and the summation of the single elements of the impulse response. So if also the summation of the impulse response is bounded, then also the output will be bounded. And this is why a condition for absolute for Weibull stability is that the impulse response is bounded. Okay? So the output is bounded if the absolute sum of the impulse response is finite. So let's be a bit more specific, and in particular, I want to give you the formal mathematical proof that a linear time invariant system is stable if and only if the impulse response is summable. Okay, this might be a question for the oral exam, for example. In the oral exam, I could ask to prove the condition for Weibull stability. And the answer is this that I'm showing here. So first, let's demonstrate the sufficient condition, okay? Sorry?
Answer for this is the whole answer.
Yes, this is the proof that you have to show. Okay, you have to know how to prove this condition for Weibull stability. Okay, so the condition. Sorry. So the condition for Weibull stability, the proof, is divided in two parts. There is the sufficiency and the necessity. Okay, because you have to demonstrate that it's sufficient, and you have to demonstrate that it is necessary that the Weibull systems are stable. That the linear time invariant systems are stable in the Weibull sense if we have that the impulse response is absolutely summable. The sufficiency of the condition is this. If we consider the absolute of the output, as I said, you can consider the absolute of the convolution, which is the infinite summation of k of h of k times x of n minus k. And this, of course, is less or equal than the infinite summation of the absolute of the two elements of the summation separately. Okay, h of k in absolute and x of n minus k in absolute. And if we have that the input is bounded, this must be less or equal than the bound of x, the maximum value of x, times the infinite summation on k of the values of h of k. And this is basically the condition on the summability of the absolute summability of h of k. So if this happens, if the impulse response is absolutely summable, it's sufficient to have the output limited, bounded, if the input is also bounded. Okay. So this is the sufficient condition. And for the necessary condition, I will prove by contradiction. Okay. So let's assume that the system is stable in the Weibull sense, although the impulse response is not summable. Okay, impulse response is not summable means that the summation on h of k in absolute is not bounded. So let's build an input sequence with bounded values. Okay. And in particular, I will build an input sequence x of n, which is 0. So the input is 0 if the impulse response is 0. And if the impulse response is not 0, the input will be the conjugate of h of minus n divided by the absolute of h of minus n. Why I will use this impulse sequence, I will explain you will understand in a moment. So let's consider the output for n equals 0. So the output in the origin. Y of 0, this will be equal to the convolution with n equals 0. So we have the infinite summation for k that goes from minus infinity to plus infinity of x of minus k times h of k. And if we substitute the definition of x of n, we have that the infinite summation on k of the square absolute of h of k divided by h of k, okay, because we are substituting the conjugate of h of minus n, okay. Since is x of minus k, substituting we have the square sum of h of k on the numerator and the absolute of h of k in the denominator. That's the square absolute. So what we have left is the infinite summation of the absolute of h of k. But this is not possible because we have obtained an unbounded output for an input which is bounded. Okay, so this contradicts the fact that the system is stable, so the output is bounded, although the impulse response is not summable. Note that the input is always bounded because we have h conjugate divided by the absolute of h, okay? So the input is always bounded by construction, okay? So since for a bounded input we have obtained an unbounded output, this proves that it's not possible to have a bibostable system if the impulse response is not summable. Is it clear for everybody? Are there any questions? If there are any, yeah. Yes. Okay, can you louder? I cannot hear.
I didn't hear the last word. You said that it's not possible to bound something.
It's not possible. What did I say? I don't know. It's not possible to have a Bible system, a stable system, if the impulse response is not absolutely summable. Okay. Okay. So let's go now to causal LTI systems. So I said that the system is causal if the output depends only on present and past values. But if the causal system is also linear time invariant, then you can study the proof, the formal proof from the lectures, and I ask you to do this. It's quite straightforward, but it's possible to prove that an LTI system is causal if and only if the impulse response is causal. So the impulse response is 0 for negative k. Okay. This is not a necessary or sufficient condition for other type of systems. So this is valid only for LTI systems. Okay. So here, what happens on the first row, what you have is the general definition of the convolution for normal LTI systems. Now, if we consider if we split in two the infinite summation, this is what you see here in the second row, in the second set of equations, you have that if the impulse response is 0 for negative k, the first of these two summations is 0, and then the rest is the rest of the convolution, okay? So from this you can intuitively see that the output will be that the system is causal because it does not depend on the past. Okay, so x of n minus k for k that is greater or equal to 0 shows only the future values of x of n. So y of n depends only on the future values of x of n. So as I said, I ask you to study the formal proof from the lecture notes. I will not spend more time on this because the proof is quite straightforward. You can study on your own. Okay. Yes, this can also be a question for the oral exam. Lastly, I don't know if we should make a pause now. How many slides are? Okay, maybe we can have a short break now, and then we can continue. We can continue later. Okay. So 5 minutes break, and then we continue. Okay, so let's go back to the lectures. Are there any questions or comments up to now? There is a microphone that is open. Okay, I'll deactivate the audio. Okay. Okay, so let me share the slides again. Okay, so to conclude a bit on the linear time invariant systems, there is another category of linear time invariant systems that is also of interest for us, which is the LTI systems that can be expressed in the form of difference equation with constant coefficients. Okay, so a generic form to describe linear constant coefficient difference equations is the one that is shown here, where you have the output combined, the combined output is equal to a certain linear combination of the input. Okay. In this form, the output is not uniquely specified for a certain input because you have to give some initial conditions, okay? And certain properties of the system are given or depend on the initial conditions that you give. If you assume that the initial conditions are 0, then the system described with constant coefficient difference equation is LTI and causal. Okay. An example of LTI system described with constant coefficient difference equation is the moving average. So if you have here the output that is a linear combination of the input, this is an LTI system and it's causal as long as the initial conditions are assumed to be 0. Okay, so if the system is at rest, then a system described with difference equations and constant coefficients is LT and causal. Okay. Let's see an example. Let's see, for example, the cumulative sum or the accumulator system, which is basically, it gives in output the sum of all the inputs up to that point in time. Okay. So you have that the output is the sum for k that goes from -infinity to n of x of k. So if we consider the 2 points, y of n minus 1 and y of n, you have that y of n minus 1 is the summation up to n minus 1 of the inputs, and y of n is the present input x of n plus the summation of the past inputs from -infinity to n minus 1. Okay, so basically you can substitute the output y of n minus 1, and you have that y of n is equal to x of n plus y of n minus 1. And if you take y of n minus 1 to the other side, you have y of n minus y of n minus 1 equal x of n. So x of n is the difference of the inputs at the present and the past. samples, okay? So we can rewrite this in the form of difference equation, where you have the linear combination of the inputs and the outputs. Okay, is it clear? So let's consider now the output of the LTI system to assign input. Okay. You will see now why this is important for us. Let's first define the input in terms of complex exponential. So x of n is equal to e to the j omega n, where n is an integer, of course. And we consider the output of the LT system as the convolution of the input and the impulse response h of k, right? So we consider the output equal to the convolution with this h of k times the input e to the j omega times n minus k, okay? And here you can take outside the part that does not depend on k, and you have e to the j omega n, and then the summation of h of k times e to the minus j omega k. All right. Now here you can notice that what you have in the parentheses here is nothing but the definition of the discrete time Fourier transform, right? So you have capital H of e to the j omega, which is the summation, the infinite summation of h of k times e to the minus j omega k. And this is called the frequency response of the system, okay? The DTFT, in this sense, for an LTE system, is the frequency response of the system. And you know that it's a complex function, of course, and it specifies the amplitude and phase change of the input. Why? Because if you look at the sign input, what you have in output is nothing but h of e to the j omega times the input, okay? So in this sense, you have that the output y of n is the multiplication of the DTFT times the sinusoidal components. So in this sense, you can say that complex exponentials are eigenfunctions of LTI systems, where the eigenvalue is the DTFT, okay? So basically, the DTFT expresses the change in amplitude and in phase of the sinusoidal input. So if you have a sinusoidal input in terms of complex exponential, the output will still be sinusoidal, but with a change in amplitude and in phase, okay? So the output is the same, but with a change in phase and in amplitude. So this is what we call the discrete time frequency response. And the frequency response defines the output for complex exponential on all the frequencies. Remember here that the frequencies are not infinite, because the DTFT is periodic, so the frequencies are either between 0 and 1, or between -1/2 and 1/2, if we talk about frequency, or in terms of angular frequency, you go from 0 to 2 pi, or from -pi to pi, okay? It's not infinite values, but still it's a continuous function and defines the output at all frequencies. And if the input can be represented as the sum of complex exponential, so if it's a combination of sinusoids, then we can determine the output of the system through the DTFT. Okay. Remember again that differently from the continuous time, the discrete time, as I said, is periodic with period 2 pi. Okay. So you have that the frequency response after 2 pi, it repeats itself, and it's always the same. Okay, here is just a formal proof, but the concept is that one. Okay, is it clear? Are there any questions, comments? Okay. So what I want to do next is to give you some exercise to do. And in particular, just some simple exercise to see if you have understood or not how it works. And I don't know if, yeah, I will give you some time. These are some problems given by the open course from Professor Oppenheim. Let me share again the screen. There you are. And let me zoom so that it's easier to understand. I would like you to try to solve these exercises. Sorry, no. Okay. So I will give you some time to do this exercise. And if there are any questions, I'm here to help. And then I don't know if we will have time to see the solution now or in the next lecture, okay? Probably the section of the book that is given here does not correspond to this edition because, again, this course was done in 1975, so maybe the last edition of your book does not correspond, but you can find the subject in the textbook easily. Okay. So the question is to show that these impulse responses that are shown here are stable in the Bible sense. Okay. So I ask you to try to solve this, to demonstrate that these systems shown here are stable in the Bible sense. Okay, I'll give you maybe 15 minutes or 20 minutes, okay? So if you have questions, just let me know, okay? So one of your colleagues was asking about the first example, h of n equal delta of n plus 2, and the question was how to prove that the system is stable, because of course, being a delta, you know that basically you're moving the sequence by a certain position, blah, blah, blah. But the formal way to demonstrate the system is stable is to write the infinite summation for n that goes from minus infinity to plus infinity of h of n, and show that the impulse response is absolutely summable. This is the formal way to show that the system is stable in the Bible sense, okay? Are there any other questions about how to proceed? Otherwise, I will give you 5 more minutes and then I will give you the solutions, okay? Okay, so sorry I was a bit late. I was talking with the students here that are in the class. Are there any questions or comments about this exercise? Did you have any problems or difficulties? Were you able to do the exercise? Can I remove this? Sorry. Can I remove this from the screen, from the sharing? I guess yes. Okay, so let me share this and I will give you the solution of this exercise. Okay. No, it's better on this side actually. Okay. So the first system was defined with impulse response h of n equal to delta of n plus 2. Okay. Delta plus 2, if we look it as a sequence h of n, and here is n. Delta plus 2 means that if the sequence h of n is always 0, okay, always 0, except when the argument is 0. So if n is minus 2, then you have the value of 1. Otherwise, all other elements of the impulse response are 0, okay? Is it clear for everybody? Is it clear for you? So, how do we prove that this system is stable? Any solutions, any clue? Any solutions? So we said that if a system is linear time invariant, the system is stable in the Bible sense if and only if the impulse response is summable, absolutely summable, okay? So to be absolutely summable, we must have that the summation for n that goes from minus infinity to plus infinity of h of n in absolute must be bounded. No, sorry, must be less than infinite, okay? So if we substitute, what we get is that, okay, here, note that there is no input in this equation, okay? We're not considering x or y in any sense. So the condition is just on the impulse response, no matter what is the input or what is the output, okay? So if we substitute in this case, so let's say in the point I, first point, we have that the summation for n that goes from minus infinity to plus infinity of delta of n plus 2 must be less than infinite, all right? So what is the result of this summation? All the elements of delta are 0 except 1, okay? So all the elements will contribute as 0, and there will be only one point, only one sample that is equal to 1, okay? Here this is 1. So, sorry. So here, let me cancel this. So here we have that this summation is equal to 1 constant. And of course, is less than infinite. This proves that the system is stable. Okay? Is it clear? Say one more time. So, since the sequence is absolutely summable, okay? Absolutely summable means that this infinite summation is less than infinite. Then, because of the proof that I gave you today about Weibull stability, the system is stable. So stable in the sense that if the input is stable, the output is stable too. And the condition, because the system is linear time invariant, is that the impulse response is summable. Okay? So here I gave you the proof that the system is stable. Okay? Now I ask you another question that was not in the text. Is this system, is it clear? Now I ask you another question. Is this system causal? Is this a causal system? If you remember, I gave you the definition, and there is a proof also, for LTI systems that are causal. It's causal Y, it's not causal Y.
In order to be polar, H of the K must be 0 for the values of the K.
Negative K, less than 0, yes. What is your answer?
No, I don't know.
You don't know, okay. Yeah, that's the correct answer. So, since h of n or h of k is not 0 for negative values, the system is not causal. Okay? So, it's easy to understand because here you have an output that depends on future elements. Okay, it depends, even if n is 0, you have delta that is already different than 0. Okay, so the system is not causal. Okay, let's see the second point. The second system was, okay, let me write it here. Okay. The second system was h of n equal to 1/2 to the power of n, u of n. Okay? So if we want to plot this impulse response, h of n, and n, what do we have here? You tell me. So for negative n, what is the value of h? It's 0, okay? Here is 0. For n equal to 0, it's 1. Okay. okay? And then all the other elements, it's a decreasing exponential. So here you have 1/2, and then 1/4, and then so on and so on until never zero, okay? So this is our impulse response. And the question is, again, if the system is stable. I want to prove that the system is stable. How do you prove this? How do you prove that the system is stable? It's the same as before. You have to show that the impulse response is absolutely summable, okay? So you have to compute the summation for n that goes from -infinity to +infinity of h of n in absolute, right? And this is equal to the summation that goes from n equals 0 to +infinity because of the step sequence of 1/2 to the power of n, right? Do you agree with this? Yes or no? Yes? Okay. So what is the result of this? You tell me. One over 1 minus 1/2, right? You all agree? Yes? So, if we want to turn this around, we have the result is basically 2 divided by 2 minus 1 equal to 2, right? So, the system is stable or not stable? What do you think? It's stable. It's stable because it's absolutely summable and this is less than infinite. So this system is stable. Is this system causal or not causal? Not causal Y, causal Y. So, what do you think? It's not causal? Why do you think it's not causal? Because? For negative n, the impulse response is 0, so the system is causal. Okay. Is it clear? Okay. And the last one. Last one was h of n equal to 2 to the power of n u of minus n. So let's see how h of n. Let's see this impulse response and the values that are taken. Here you have 2 to the power of n times u of n, u of minus n, sorry, u of minus n. So you tell me what are the values of this sequence. Can you show me, for example, for n equals 0, What is the value for n equals 0? 1, okay. 1. For n greater than 0?
0, 0.
Okay. And for n negative?
Negative is exponential.
Is the same, but flipped over.
Positive exponential.
Exactly. So here you have 1/2, 1/4, and so on. Okay. Okay, so how do you prove that this system is stable? We do the same, right? So here you have this infinite summation for n that goes from -infinity to +infinity of h of n. What is the result of this summation?
Is the summation from n equal -infinity to 0.
Okay.
And the summation from -infinity to 0 or to 2 to n.
Yes, 2 to the power of n.
2 to the
Okay.
power n.
Okay.
And is equal to
Okay, I think that the result will be 2. Do you agree with me or not? You tell me.
I think it's -2.
You think it's -2? Okay, show me. Prove it, and then you show me. So try to compute yourself and tell me what is the result of this summation, if it's stable, if it's not stable, and so on. Non è sicuro se lo scriva. If you're not sure, do the computations. Come? Non ho sentito. Faccia i conti.
Io abbiamo scritto un mezzo abbiamo scritto come 1 su 1 nel mezzo, viene dalla regola, da quello che abbiamo visto prima, tutto dalla...
Non nella progressione geometrica, questa è la serie geometrica, è una serie che va infinito. Questo se lo dovete passare perché...
sì, questa serie geometrica quindi...
Did you find the result?
The legend is going for minus 1 and half of minus 1.
Just a second, I will talk with the student. Fine. Yes, this is the, remember the increase. So n here, it's not negative in general, it's negative here. This one. So the summation goes from minus infinity to 0. I mean, it goes to plus infinity, but all these elements are here. Is it clear for you? It's clear? It's quite simple, because you should do the summation from minus infinity to plus infinity, right? But all these are zero. So we can start from minus infinity to 0. Is it clear from home? La calcolatrice si sta con la calcolatrice sta facendo il conto. Ah, ok.
Dovrei fare una serie geometrica.
Ok, va bene. Ok. Sei riuscito? Un po' arrugginito. Okay, so why it is 2? Because you consider the infinite summation from n that goes from minus infinity to plus infinity of 2 to the power of n u of minus n. But this, we said that it's 0 for n positive. So you have the summation that goes from n that is minus infinite to 0 of 2 to the power of n, right? But we don't know how to solve this. However, if we change variable, if we change the variable of the summation, we can write summation on m that goes from 0 to plus infinity of 2 to the minus n, right? which is exactly the same summation as before. Okay, so it's exactly the same summation, and the result is 1 minus 1 minus 2 to the minus 1, or if you do all the computation, is basically 2. Okay, all right. So the system is stable. You agree? If you don't agree, I can give you the proof again. I'm joking. Is this system causal? Is this system causal or anti-causal? What do you think? It's not causal because n is not 0 for negative values. H of n is not 0 for negative values. Okay. Let's see now something else. Let's see if we have some other exercise. Okay. Let's see these few exercises and then we will stop for today. Now that you have understood a little bit how it works, okay. So now the question is to determine if these systems are stable and or causal. Okay. I give you 10 minutes maybe, or 10 or 15 minutes to understand if this is to say if these systems are stable or causal. Okay. Okay, so a few more minutes, or maybe, I don't know if you have already the solutions. You have any idea, any clue? Do you have already found the solution?
I think the first one
Mm-hmm.
is looking bounded, but I wouldn't make it so maybe bounded or not, so it's not stable.
Mm-hmm.
The second one, the value of A is from A0 to N, so it's bounded, it's stable.
Mm-hmm.
And the third is not stable because it depends, I mean, we don't know from where a value will be from to where. That's my question.
Okay. So the first thing to note here is that these systems are not necessarily LTI systems. Okay. So you cannot apply the proof that I gave you before, because the proof for absolute summability is for systems that are linear time invariant. Okay. So how do you solve this problem? Let me share the screen again. I don't know. Are there? Okay, sorry. Let me share the screen. There we are. Okay. So this is the exercise 3.3. This is the 3.3 in the Oppenheim-Schaffer exercise, okay? You can find these exercises online and also the solutions online, okay? So the first function was y of n equal to g of n x of n. Okay. And we know that g of n is bounded, okay? Now, the question for the system to, let's start first from the causality. Is the system causal? This is easier to know. It's causal because it does not depend from the future, okay? It depends only on the past values of the inputs, okay? So it's causal. This was easy. It's stable. Stable in the Bible sense. Stable in the Bible sense means that if the input is stable, the output is also stable. If the input is not stable, who cares? Okay? But if the input is stable, the output must be stable. Okay? Now, we know that g of n is bounded. We don't know about x of n. So, since g of n is bounded, if x of n is bounded, the output will also be bounded, right? This is already enough to say that the system is stable, because if the input is bounded, the output is also bounded. Okay, so the system is stable. Stable, bounded. Sorry, not stable and causal. Okay. Okay, so let's go now to the second one. This was A, B, y of n equal to the summation for k that goes from n0 to n x of k. Okay, so what about this system here? Is this system causal first? It's causal because it does not depend. We assume here that n0 is less than n. Okay. Sorry. Why is not causal? It's causal or not causal? Sorry? So the first question, I'm assuming here that n0 is less than n for simplicity, okay? So the system is causal or not causal in this case? It's causal. It's causal, do you agree?
Yeah.
Okay. It's causal because it does not depend on future n, but only from the past, because n0 is less than n and all depends on the past. Okay. So it's causal. What about the stability? No. Stability means that if the input is stable, the output is stable. Sorry, if the input is bounded, the output is bounded. So, what do you think? It's stable? Stable? Do you agree or not?
Not really.
So we are assuming. Come on. Sorry. Okay. We are assuming that if x of k is bounded, p of x less than infinite, we want to know what about the output. Okay.
Ma dobbiamo assumere che sia bounded, sia bounded.
No, not necessarily. Stability in the Bible sense means that if the input is bounded, then also the output is bounded. It's a consequence. Okay? This no. Means we're saying that if the system is stable, if this happens, then y of n is bounded less than infinite. Okay. Now the question is this true or not? Yes, why? No, why?
Because if I found something that is bounded, it's bounded.
Is also bounded.
The sum is bounded.
Okay. You agree or not? Yes? Okay. So this is causal and is stable. Okay. If it's not if the input is not bounded, who cares? But if it's bounded, the output must be bounded too. Okay. Let's see the last one. The last one is y of n equal to x of n minus n0. Oh, is it causal or not causal? Let's assume that n0 is positive. n0 is greater than 0. So that is simple. It's causal or not causal? It's causal. It's stable or not stable?
Because the input is zero, so basically the output is also stable.
Wait, why the input is 0? No, the input is not necessarily 0. I'm just assuming that n0 is greater than 0. Okay, this is just the position in time, the shift in time, but the sequence is always x. Okay, so the question is the same. I will write it here. If the input is bounded, the output is also bounded. Yes or no? What do you think? Stable or not stable? Yes or no? Not stable. Why? Stable, why?
It's not bounded.
Why it's not bounded?
It doesn't describe or it doesn't show anything like bounded.
We don't know if the input is bounded or not. The input is x, we don't know. But if the input is bounded, how is the output? Is also bounded, right? So the system is stable in the Bible sense. If the input is bounded, then the output is bounded, and it's a stable system. If the input is not bounded, maybe the output is not bounded, but it's no problem. If the input is not bounded, it's no problem. So it's also stable. All right? Is it clear for everybody? Any questions, comments?
Sorry, I have a question.
Yes.
If you're right, even if the system is polarized, I mean, if it's stable, it can't be polarized or not polarized.
Not. It's two different things.
Yeah, if the system is polarized, would it be stable or not stable?
We don't know. It's two completely different things. Okay. If you remember the example here, you have two systems. One is causal, one is not causal, and both of them were stable. Okay. The causality has no impact on the stability and vice versa. Okay. Okay, I think we can stop for now, and then we will continue on Tuesday next week. Okay. Any questions from home? Any comments? Okay, so see you in 2 days. Goodbye.